Alright, welcome back. In our last video, we found an equivalent system in row-echelon form, and in this video we're going to continue this example by trying to find the solution set using back substitution, and we'll also check our original system of linear equations with the solution set to see if it's valid for that system. And if it is, remember, then that means that system is equivalent to this new one, this boxed one here. So back substitution is pretty easy. We start at the bottom and we plug in the known variables into equations above them to solve for the other variables. So here we know that z is equal to 2. So if we look at the second equation, equation 2, we have y minus 4/3 times z, which is 2, is equal to negative 2/3. So this simplifies down to y minus, 4/3 times 2 is simply 8/3, and that's equal to negative 2/3. And if we add positive 8/3 to both sides, we'll get y is equal to negative 2/3 plus 8/3, and 8/3 minus 2/3 is 6/3, and 6/3 simplifies down to 2. So we solve for y. That means y is equal to 2. So we have y equals 2 and z equals 2. So now if we look at equation 1, we have x minus 2y, y we found out was 2, minus z, which was 2, and that's equal to negative 6, right? So x minus 2 times 2 is 4, minus 2 is equal to negative 6. And finally, x minus 4 minus 2 is minus 6, and that's equal to minus 6, right? And if we add 6 to both sides, we have x is equal to 0. Cool. So the solution set to this equivalent system of linear equations is x equals 0, y equals 2, and z equals 2, right there. So, since we performed elementary row operations on each one of these equivalent systems, this long set of equivalent systems, then that means that solution set that we found, x equals 0, y equals 2, and z equals 2, should satisfy all of these systems. But just to check, we're actually going to plug in that solution set into this original system of linear equations to see if it's satisfied. So I'm going to scroll all the way down, and I'll go ahead and rewrite the original system here. And what we're going to do is we're going to look at each one of these equations, and we're going to plug in this solution set to see if all three equations are satisfied. If they are, then that means the solution set that we found here satisfies this system of linear equations, and that the equivalent system that we found here in this pink box is actually equivalent. So let's scroll back down and let's do that. Let's look at equation 1 first. So negative 3x, x is 0, right? Plus 6 times y, y is 2, plus 3 times z, z is 2, right? And that's equal to 18. Well, negative 3 times 0 is 0, plus 6 times 2 is 12, plus 3 times 2 is 6, and that's equal to 18. Well, 12 plus 6 is in fact 18, right? That's equal to 18, so the first equation checks out. Let's scroll down a little bit more and let's check equation 2. Equation 2 is negative 2 times x, which is 0, minus 2 times y, which is 2, plus 10 times z, which is 2. And that's equal to 16, right? Well, negative 2 times 0 is 0, minus 2 times 2 is 4, plus 10 times 2 is 20, and that's equal to 16. Well, negative 4 plus 20 is 16, and that equals 16, so that's good. And finally, our last equation, equation 3, 4 times x, which is 0, plus y, which is 2, plus 5 times z, which is 2, that's equal to 12. Well, 4 times 0 is 0, plus 2, plus 5 times 2 is 10, that's equal to 12. 10 plus 2 is 12, and that equals 12. So that checks out. So great, that our solution set, which was x equals 0, y equals 2, and z equals 2, does in fact satisfy the original system of linear equations. So we did something right. Now what I'm going to do is I'm going to actually take this equivalent system, this one here in the pink box, and I'm actually going to go to my graphing software. And just for the sake of time, I've already entered in these three equations, that equivalent system of linear equations here. And you'll notice that this is obviously a 3D graph. And each one of these three equations are plotted as planes here, right? So what's cool about this is that since we found a solution set, we know that this solution or this system of linear equations has a consistent solution. And that means the graph or the planes of these three equations should intersect at some point, right? And if you look closely, it looks like they do. It's somewhere around here. So what's neat about this is that I can take a cut of all three of these planes, and you'll notice that if I move this graph here, you can see that the projections or the cuts for these planes all intersect right about there. Do you see the three lines intersecting? So if we were able to get those values off this graph, then they should be x equals 0, y equals 2, and z equals 2. And you can always check this using any one of your graphing software to kind of verify that you did the algebra correctly, right? And finally, there's one more thing about this solution set. So since we used elementary row operations on all of these equivalent systems of linear equations, you can actually plug in this solution set into any one of these systems. So if you're bored one day and you really didn't have anything else to do, you can plug them into each one of these systems and see if all the equations in each of these systems are satisfied. Since we used elementary row operations to convert one system into an equivalent system and that system into another equivalent system, they should all be verified. Sounds like a ton of fun, right? But it is a pretty good habit to check your equivalent system as well as your original system with the solution set to make sure that all the equations in all these systems are satisfied.